Let's begin with a quick review of what we know about integration so far. And most of what we know about integration comes from what we know about derivatives. So for example, I know that the derivative of a power of x is equal to that power times x raised to a power of degree 1 less. That implies that if I wanted to integrate x to the n dx, then instead of decreasing the power by 1, I would increase the power by 1 and then divide by the new power, and of course add a plus c. I also know things like the derivative of the sine of x is equal to the cosine of x, so that would imply that the integral of the cosine of x dx is equal to the sine of x plus c. All right, so today I want to look at things where if I had taken the derivative, I would need to use the chain rule. So what about if I wanted the derivative with respect to x of the sine of x squared? Now the chain rule says take the derivative of the outside and leave the inside alone. So that would be the cosine of x squared, and then multiply by the derivative of the inside, which is 2x. So that implies that if I needed to integrate 2x times the cosine of x squared dx, then that should be the sine of x squared plus c. And I think it's pretty easy to see that if the derivative worked out like this, then the integral would end up working out like this. But what if the conversation started where we only saw what the integral was? So this is integrating where we're dealing with composite functions. So let's consider that same example again. I want to integrate 2 times x times the cosine of x squared dx. And the thing that we will recognize here is that we have a composite function. There is a function inside of another function, and then there maybe is some other stuff hanging around, and we will deal with that other stuff as we go along. What I'm going to do is what is called a U-Substitution. And the idea is that I'm going to change the variable from being in terms of x to being in terms of a new variable, u. So I will start by letting u be with that inside function. I'm going to let u be equal to x squared. So now u is a function of x, and I'm going to take the derivative of u with respect to x. So du dx is going to be equal to 2x. And then what I will do is I will multiply both sides of this by dx. So I get that du is equal to 2 times x dx. This right here is what is called a differential. A differential is where the du is on one side and the dx is on the other. And so I'm going to change now this integral to be in terms of these new variables. What does this say? It says that everywhere that I see an x squared, I'm going to change that to being a u. And everywhere that I see a 2x dx, I'm going to change that to being a du. All right, well right here, I have a u because that's x squared. And then if I look at this piece right here, the dx and the 2x, that is going to change to du. So this new integral is now the integral of the cosine of u du. You may want to pause there and look at that and make sure that I have substituted everything that was in there in terms of u. So now what I've done is I've created a new integral that's a lot easier for me to deal with. I know how to integrate the cosine of u. That is the sine of u plus c. Now, I changed it into the variable u. I want to change it back into the variable x. So I take advantage of the fact that u is equal to x squared to make this be the sine of x squared plus c. And that gets me back to where I started. All right, there's no way that you can see one example of this and think that it's clear, so let's look at a couple more examples. How about the integral of 2x times x squared plus 5 raised to the 4th power dx. So you may look at that and say, you know, we could integrate that, because certainly I could take x squared plus 5 and raise it to the 4th power. That'd be a little bit of ugly algebra, but you'd be able to do it. And then you could multiply the 2x into that polynomial, and then you'd have a big polynomial, and you could integrate that. But what I want to do is recognize that the derivative of this inside function is on the outside. That is an indication to us that we would like to use a U-substitution. So I will let u be the inside function, x squared plus 5, and then I will take what we called before the differential. That is that du is equal to the derivative of x squared plus 5, which is 2x, multiplied by dx. Now, everywhere in the integral that I see an x squared plus 5, I'm going to put a u, so that's going to go here. And then everywhere that I have a 2x dx, which is here and here, I'm going to replace that with du. So this whole integral is going to become the integral of u to the 4th du. You can see that this u substitution made the integral a lot nicer. There's a lot less stuff going on. And this also becomes an easy integral to do because it is just the power rule. So u to the 5th divided by 5 plus c. And then I want to put this back in terms of x. So wherever there is a u, I need to put an x squared plus 5. So x squared plus 5 raised to the 5th power divided by 5 plus c. As usual, I can check and make sure that this answer is correct. Let's do that. If I take the derivative with respect to x of my integral, x squared plus 5 raised to the 5th power divided by 5 plus c, clearly the c is going to go to 0. Now, this is the chain rule, so I would bring the 5 in front, so that would be 5 times x squared plus 5 raised to the 4th power, all divided by this 5 here. And then I would have to multiply that by the derivative of the inside function, which is 2x, and the plus c goes to 0. Here the 5's are going to cancel, and I could rewrite this as 2x times x squared plus 5 raised to the 4th power. And I can see that the derivative here matched what my original function that I was trying to integrate would be. Okay, let's look at another example. How about the integral of x squared divided by x cubed plus 7 dx? Now here it may not be so obvious that I have a composite function, but I can think about the function that is in the denominator as being a function that is inside of another function. So I will let u be x cubed plus 7, which means that du would be 3x squared dx. Now everywhere that there's an x cubed plus 7, I'm going to replace that with u, so this denominator is going to become u. And then everywhere that there is a 3x squared dx, I'm going to replace that with du. Now you may notice here that I don't actually have 3x squared dx. I have only x squared dx. So it's a case where the derivative isn't there. The derivative of the inside function isn't on the outside in this integral. The fact that it's off by a constant is okay, because in this equation right here, I could divide both sides of the equation by 3. Those 3's would cancel, and now wherever there is an x squared dx, I can replace it with du over 3. So that allows me to rewrite this function, or this integral, as the integral of x squared dx is a du, and then 1 over x cubed plus 7 is 1 over u. And then, of course, I had a 3 here, so this is du over 3. I could rewrite that integral with the 1/3 out in front and have, oops, I was getting ahead of myself there. I would have the integral of 1 over u du. So I get 1 over 3, the natural log of the absolute value of u plus c. And then since u is equal to x cubed plus 7, this will be 1/3 the natural log of the absolute value of x cubed plus 7 plus c. I encourage you to pause this video right now and take the derivative to check and make sure that that worked. Let's look at another example. My next example, let's look at the integral of x times the 4th root of x squared plus 1 dx. The key thing that you will be always looking for is what function is inside of another function. Here, x squared plus 1 is inside of the 4th root. That is usually a pretty good guess that you want u to be equal to x squared plus 1. Then, let's follow it through. Du would be equal to 2x dx. And then I look at what I have. Do I have a 2x dx? No, but I do have an x dx. What I'm missing is the 2. So if I divide both sides of this equation by 2, I get that x dx is equal to du over 2. Make the appropriate substitutions. This would be the integral of the 4th root of u, and then x dx is equal to du divided by 2. I could rewrite that integral as 1/2 the integral of u to the 1/4 du, which would be equal to 1/2 times u to the 5/4, 1/4 plus 1, divided by 5/4, which is multiplied by 4 over 5, plus c. Let me clean that up a little bit. 2 goes into 4 twice. So I have 2 over 5 u to the 5 over 4 plus c. And then if I resubstitute back in for x, 2 over 5 times x squared plus 1 raised to the 5 over 4 plus c is my integral. And again, I encourage you to pause and check the derivative of that to make sure that it does work. All right, one last example. How about the integral of the sine to the 4th power of x multiplied by the cosine of x dx? May not be obvious in this one because of the fact that we're dealing with trig, but right here I have a sine that is being raised to the 4th power. That is the indication that lets me say that u should be equal to the sine of x. If I follow my pattern, du will be equal to the cosine of x dx, and the cosine of x dx is right here. So now the integral becomes the integral of u to the 4th power times du. This, of course, is using the power rule, so u to the 5th over 5 plus c, and then I substitute back in terms of x, and I get the sine to the 5th of x divided by 5 plus c. I'll go ahead and check that derivative. D dx of the sine to the 5th of x all over 5 plus c. Obviously, the derivative of c is going to be 0, and so the derivative of sine to the 5th will be 5 times the sine to the 4th of x times the derivative of the inside, which is the cosine of x, and all of that is divided by this 5, and those 5's are going to cancel, and it leaves me with sine to the 4th of x, cosine of x.